Okay, so today we're going to learn about integrals. And the gist of what an integral is finding the area of a function. And it might seem like, why is that so important? And it becomes very important once it's linked with derivatives, because integrals and derivatives describe nature, because things in nature change with time. So in this video, we'll just go over what the definition of an integral is, and then in a later video, we'll connect derivatives and integrals together. Okay, so I think it's best to start with just an example. So let me draw a coordinate system. And let's say that there's a function f of x is equal to, let's just say, 4. So that means that for any value of x, y is going to be 4. So in order to find the area of this function, let's say from x is equal to 0 to x is equal to 5, it's pretty trivial. We just have to multiply the length in x by the height in y. And so the length in x is going to be 5, while the height in y is going to be 4. So the area is 20. Yeah, so the area. So this one is pretty trivial, but now let's do another one. So now let's say that our function is described by this. F of x is equal to x. So 1, 2, 3, and then 1, 2, and then 3. So let's say that we want to find the area from x is equal to 0 to x is equal to 3. This one is a little less trivial. We cannot just do distance in x times distance in y. But since this looks like a triangle, which it is, we can pretty much follow the same method, but just divide the total area in half, because that's the formula for the area of a triangle. So change in x, change in y, and then divide it by 2, and we get 4.5. Okay, so for these graphs, finding the area wasn't too bad, because these areas were modeled by polygons that we're familiar with, such as a rectangle here or a triangle. But now let's go to an example where problems start to arise. So this function is going to be a quadratic function. And okay, so this function is going to be the quadratic function. So we'll just write the function up here first. F of x is equal to x squared. And now, if we want to find the area from x is equal to 0 to x is equal to 3, how will we do that? Since this is a curve, there is no polygon that models this curve that we know the formula of an area of the area to. So we can't go to the normal polygon route like the previous two examples. So we have to come up with ways to estimate this area now. And one way to do that is to use the Riemann method, the Riemann integral method. So this is one method that integrals are modeled after. And what this method does is splitting this function into rectangles and then taking the area of those rectangles. So let's say that we make a rectangle from 0 to 1. So that's the width of the rectangle. And then we want the height of the rectangle to be on the right side of the x value that we take the width from. So the right side of this width is going to be 1. So we go up to the value of 1, and then we just make a square from that. And then we do the same thing here. So if our width is from 1 to 2, we take the y value of 2, and then we draw a rectangle here. And then the same thing for this. So yeah, these rectangles all have equal width, but their height is modeled by the right side. So if you could see, this gives an estimate of what the total area is under the curve. But there is an error, and the error is within this area. This area doesn't actually represent the area of the curve. This is extra area that is an error in our estimate. So one way that we could fix this is to make smaller rectangles. So now, instead of having 3 rectangles, what we could do is have 6. So imagine if we did the width of the rectangle, not having 1 wide, but we did half. We did 1/2 the width. So here, that would look like that. And then we use the same methodology. We take it from the right side. We take the value of y on the right side of the rectangle. So yeah, this is what it's gonna look like as we keep adding rectangles. And yeah, this is gonna be somewhere around here. If the y values are not accurate for all the rectangles, I apologize. I'm kind of just estimating based off the shape of the graph. But if you could see, the error that we're getting is getting less. There's less area outside for our error. And we could keep doing this. We could instead go to 1/4 of the distance in x. So we could split all of these rectangles again into half and then keep going. But the trend that's important is that the area that is being estimated from these rectangles are getting better and better as we keep adding more rectangles. And this is an abstract concept that is best modeled by an equation. So the area of f of x can be modeled by an equation that we could come up with based off of this rectangle concept. So we know that we should have some kind of summation because we want to eventually add the areas of all of this. And we know that we need to keep in mind the y value, the height of each one of these rectangles. And the way to find the height, actually, before we find the height, I think it's more intuitive to find the width. So let's say that from 0 to 3, we want to have one big rectangle first. So one big rectangle would look something like this, right? This is a bad estimation, but this is a starting point. And the width of this big rectangle, let's say that okay, so this concept of adding rectangles that keep getting smaller and smaller to improve the estimate can be modeled by an equation. So we try to come up with an equation that best models this concept. So the area of f of x can be modeled by an equation that we come up with below. And so we know that since we're adding the area of a bunch of rectangles, there should be a summation. And the next thing we know will happen is a number that defines how many rectangles there are. And that number is going to be the number n. So whatever we plug in for this number n is how many rectangles there are that will estimate this graph. So one easy starting point is to have one big rectangle. So from the starting and end point of the interval that we want to take. So imagine that n is equal to 1. This is what we're going to get. And based off of this, we have to find the width and the height that we want for this rectangle. So I think the more intuitive thing to do is to find the width. And one way to find the width is the final point minus the initial point over the number of total rectangles we have. So in this example, the final point is going to be 3, and the initial point is going to be 0. So that's the total interval that we want. And then n is the amount of rectangles that we have. And here, since we have only one rectangle, the total width is going to be the entire interval. But imagine we have 4 rectangles. Then the width of each one of those rectangles is going to be 1/4 of the entire interval, if that makes sense. So here is the width. So then now let's think of how we could find the height of each one of these rectangles. So since we're taking the value of x on the right side to find the height, what we could do is we could just plug in the x value into the function. Because when we plug in the x value into the function, we get its corresponding y value. So let me just, it should be not f of x, but it should be f of the starting point, a, plus b minus a over n. So what this means is, since a is the starting point of this interval, so in this case it's going to be 0, and then the final point is going to be b, we start with the starting point, but then b minus a over n is the width of each one of these rectangles. And in order to traverse these rectangles, we have to add another variable, and let's just name it I. And this variable will be in the front. So I is equal to 1. So let me just summarize this real quick based off of the one big rectangle example. So for this big rectangle, we have 1 for n, big N, and then b is 3, and then a is 0 over 1. So this is the width of the entire rectangle, which is 3. That's what we expected. And then now for the height, since we started at a, which is 0, we have to add the amount of x value that we traversed, because the amount of x value that we traverse gives us the rectangle that we're at. And since we only have 1, b minus a over big N is just going to be 3. So a, which is 0, so 0 plus 3, it's going to be f of 3. And f of 3 is up here. So we just created this big rectangle. But now let's do a, I guess, more complicated one. Imagine we have now, imagine we do it with these purple rectangles. So n is going to be 3 because we have 3 purple rectangles here. And b is still going to be 3 since that's the endpoint of our x. A is going to be 0. Big N is going to be 3. And then we just keep plugging in. And yeah, and then now we could see why I is necessary. So for the first rectangle, the width never changes as we traverse these rectangles. It's always going to be, in this case, just 1. And then as we traverse through I, which represents the rectangle that we're at, let's say that we're at 1. That means it's our first rectangle. We get 0 plus 1. So that's 1 is going to be plugged into f of x, and that's going to be our height. So the first rectangle is going to have 1 times 1, and that's what we expect, an area of 1. And then the next rectangle is going to have a width of 1, and then we move over 1 more, right? Because that's what I does. And then we're going to now have a width of 1 times a height of 4. And then the same thing here. So that's how this formula works. But how do we abstract this entire concept into adding more and more rectangles, where the estimate becomes so good that the area that we're estimating with these rectangles is the exact area of the function that we want under the function? And we come back to the idea of limits again. So yeah, so then this entire function can be put in a limit. And then what should we take the limit of? So which one of these variables should we try to increase as much as we can? And that variable is going to be big N, because big N describes how many rectangles there are. And we want to increase big N all the way to infinity. Because once big N approaches infinity, then there's going to be so many rectangles here where the error on the outside here that we see is going to go away, since it's going to be like boom, 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 boom. Here, let me use another color. So it's going to just be a bunch of little rectangles like this, which, if you just see visually, it's just drawing out the area of a function. So yeah, let me just write it clearly. The last thing that we came up with, which is the full formula now of this is the like Riemann integral approach. So it should be b minus a over, let me add the summation. Yeah, so the summation n, the number of rectangles, I is equal to 1, and then b minus a over big N. This is the width, and f of a plus b minus a over big N times I. Yep, so this here is the definition of an integral. So yeah, let me just summarize real quick. The reason why we need this idea of how to find an area under a graph, and we need the idea of an integral, is because some graphs we cannot model based off of just ordinary polygons that we're used to, like a square or rectangle. Some graphs have a curve in it, like the quadratic function. And in order to find the area under this, we have to take the limit, which helps us add infinitely many rectangles to approximate the area under here. And the approximation becomes equal to the area under here once big N, the number of rectangles, goes to infinity. And I guess the idea of a limit being able to go to infinity, and then I guess, I don't know. I guess the way to think about it is whenever you use a limit and you end up taking it to infinity, the estimate becomes so good that it is the real value. That's the same for a derivative and the integral. So yeah. All right. Thank you.